Hello everyone, welcome to my presentation. I am Karthika and I'm doing my master's in data science. And today I like to present my dissertation on the topic machine learning prediction for droughts using weather and soil data. So let me walk you through my research. So the aim of my research is to develop accurate predictive models that can help you predict the occurrence of droughts. So the main objectives are to collect the data necessary for this prediction, so which includes weather as well as soil data. And then my objective is to also identify the machine learning algorithms which would be suitable to carry out this task. I would also then validate and test these different machine learning models based on the data, the historic data of weather and soil conditions that I've collected. I then also evaluate the performance of these models, especially the top models that I have found. I would be evaluating them locally on my machine as well as on a cloud-based platform. I then deploy, my objective is to then deploy the best model as a web application and then also to develop some kind of visualization tool to present my findings and insights. Moving on to the next slide. So my data was actually sourced from Kaggle. Kaggle is a very famous data science competition platform, and they also provide public data sets. So this data is actually US drought meteorological data, and it was actually obtained from NASA Langley Research Center. It's based off one of their projects. And apart from the meteorological data, an additional data set for soil characteristics is also involved as part of this research. So the data set that was used in this research was already split into training, validation, and testing data. So if you could see here, there is approximately 19 million records in the training set and 2 million, approximately 2 million each in validation and testing set. And the number of features in the meteorological data set is 21, whereas for the soil set, it's approximately, it is 32 features and there is 3,000 rows for the soil set. Now, when it comes to this research, it's a classification problem. So the target variable, the variable called score, is what determines the drought category, the level of drought. So as you can see here, based on this table that we have, the drought level are categorized into D0, D1, D2, D3, D4 based upon the description given here. So in the data set, these drought values, the score values are, they range from 0 to 5, 0 being absolutely no drought. So that's how the data structure looks like. And then when we move on specifically to the data, to the meteorological data and the soil data. So meteorological data, it contains several indicators of weather, like the wind speed, the humidity, temperature, surface pressure, frost point, precipitation, and so on. But these are also recorded at different levels. Like for example, wind speed at 20 meters, minimum wind speed at 20 meters, minimum wind speed at 10 meters, and so on. It also records maximum and range of temperature at 20 meters. So that's how there are like 18 indicators of the meteorological data. Also, for soil, we have the slope characteristics of the soil. They also consider the land type of the area of the land that we're predicting the drought for. For example, it could be forest land, it could be grassland, it could be a residential area. They're also looking at the rooting conditions, the nutrients in the soil, the oxygen availability, and so on. So apart from these characteristics, there are also a set of features that are common to both meteorological data and soil data. For example, the FIPS code. The FIPS code is actually a US county code, which we later discuss again because that's based on what we merge the meteorological data and the soil data. Moving on to the data analysis part, I've done quite a few plots. We have density plots here. We have density histograms, a scatter plot. I have not included the diagrams for all the plots that I've done because there is 18 to 32 features and I've done it for all of them, but I've included few. This is for precipitation. It's a density plot, and we have a box plot density histogram here for QV2M is actually the specific humidity at 2 meters. And then I have a scatter plot here to identify the variation for temperature at 2 meters and specific humidity at 2 meters. I also have the correlation metrics here for weather features, weather the meteorological data, and you can notice that there are quite a few features with a good level of correlation. But as I've found that there is a certain amount of variance, I'm retaining all the features as of now, and then as part of the algorithms that I choose, I implement certain feature elimination or feature selection methods along with the algorithms rather than selecting out features before I implement any algorithm for my model. And for data pre-processing, I have handled the missing values. So a fact about this data set is that the data is being collected every day. So the meteorological indicators are being noted down every day, but the drought score is available only once during a week. So when you look at the data, there are so many rows of data without a drought score because the drought score is available only once every 7 days. So all of that data without a drought score is absolutely of no use to the research. So they have been removed. So the missing values have been removed, and there was a feature with date which was stored as an object. So the month, day, and year has been extracted from it, and outliers for all the features have been removed using the 3 sigma rule. So basically, we're just removing all the rows that do not lie within 3 standard deviation of the mean. So that is the 3 sigma rule. And then I have joined the weather dataset, the meteorological dataset, and the soil dataset based on their common attribute, the FIPS code. So the FIPS code is common, which is the US county code. It is common. It is present in the meteorological dataset as well as the soil dataset. So I've merged the two dataset with the help of the FIPS code. Then I've converted the target variable, the score variable, to an integer type for predicting the score better. And I've done scaling. I've done scaling based on the training data set. I've fit the test data set and the validation data set. I've scaled them. And I also deal with data set imbalance. So there is an imbalance of data here. The number of data with a certain score is significantly higher. It tends to be higher towards lower drought score. So I've dealt with them as well, but that is also handled as part of my model rather than being done before deciding my model. So I've done SMOT, I've done upsampling and downsampling somewhere, but that's all done as part of my model. So it comes with the model. Now, these are the algorithms that I've used for modeling. I have used random forest. There is about 14 models that I've used: random forest, AdaBoost, XGBoost, decision tree, k-nearest neighbors, ANN. So I've trained some of the models on the whole dataset, while some of them are trained on a smaller dataset because it was computationally very exhaustive and I couldn't carry out the training on the complete dataset. So this was the metrics for the whole dataset, and ANN seems to have the highest accuracy among this. While I did the training for a smaller subset for 0.1%, which is still around 19,000 data. And random forest with RFE and grid search was the best performing model here. So then I took the top 3 models and I compared them. I compared the runtime in my local environment as well as the cloud environment. So as you can see, most of the times the runtime was reduced to half in the cloud. And when it comes to ANN, it was the difference was very, very significant. It took about 11 hours on my local system, and it took just 67 minutes on the cloud. So these are the instances, the SageMaker instances that I used to run the model on AWS. So I performed the training, testing, and everything on SageMaker instances. So I deployed the model, the highest performing model, the random forest with RFE, recursive feature elimination, and grid search CV for hyperparameter tuning. I deployed it using an endpoint. I stored my packaged model in S3 bucket, and then it was deployed with the help of APIs. So this is how I stored my model in S3 bucket on AWS. My model is deployed here. And then I tried to make a web app. I wanted to make a web app which lets you upload an Excel file with your test data. And then the deployed model kind of processes the data and then displays the result. So this is how it's a very basic, simple web interface. So it lets you upload the data and then the results should be displayed. Sorry. So if you can see, it shows the logs of your dataset being read, my pre-processing steps, date extracted, just all the pre-processing steps that I explained previously, scaling. And then if you could see here, my predictions are made, performance metrics, it's calculated, it's here, the accuracy is about 76% here for my deployed model here. But unfortunately, this is something I am keeping for my, I'm still working on displaying the results directly on the web page, but as of now, it could be very clearly read from my logs. But something I'm keeping for the future is to make the web interface a little bit more user-friendly, and then the results, the display of the results being very well clearly displayed on the web page. So this just the technology stack, the local environment that I have, and the software that I used Python for coding. I used Jupyter Notebook and Anaconda. These are the libraries that I've used. I've used Pandas, NumPy, scikit-learn, Matplotlib. And for the cloud environment, I've used Amazon Web Services. These are all the instances that I've tried to test my models. Quite a few here. I've used against Jupyter Notebook in SageMaker. I have used the same. I've used Poto3 and ngrok and Flask to deploy my application. I've used S3 buckets to store my data and CloudWatch to monitor my logs. The future work, as I've said before, is to make real-time predictions as well as to make a better user interface for my web application. This is the conclusion part, my best performing model, comparison of my runtime and my model deployment. So thank you for watching my video. Have a great day. Thank you.